So first of all, a little review of finding the inverse of a 2 by 2, because you're going to have to know how to do that on the non-calculator part. All right, so what do? First, we find our determinant. This arrow would be 6, this arrow would be 5. 6 minus 5, our determinant would be 1. Once you have the determinant, the inverse is 1 over the determinant, which you don't have to write that, but just to remind yourself that that's there. Then the one diagonal we switch, and the other diagonal we make negative. This is one way to find the inverse. It's not a very hard way. It'll probably be the way that you use the most. But today, we're going to find out that you can use Gaussian-Jordan elimination to find inverses of anything. Like, remember when we got to the 3 by 3 and I said the formula for finding the 3 by 3 was very complicated, so we don't do it. But we can use Gaussian-Jordan elimination to find it. And the way that it works is that you take your original matrix, so we already know what the inverse of this one is, and we set it up like an augmented matrix, but we put the identity matrix on the other side. So our job right now is to have the identity matrix on the left, and if we do row operations with that, whatever happens to be left on the right will be your inverse. So again, what do we want to get first? First, we want to get this to be a 0. Okay? So I can take row 1 and minus 2 row 2's and make that a 0. But now I have to do that all the way across. For each one. Next, I may as well just make this into a positive 1. So I can take row 2 and multiply that by a negative 1. So the bottom is good. Can you see already that it made that one? I mean, we know the determinant is 1 in this one. When the determinant is any other number, this method gets somewhat frustrating because you're going to get fractions everywhere. Because normally if the determinant is 3, you'd have that 1/3 out in front. But in this method, all of those fractions would be built into the question. But can you see that we already had the negative added to that 1? And that 2 and the 3 have to switch. We've already got the 2 in the bottom corner. Next, we want to get this to be a 0. So we'll change row 1 to row 1 minus 5 row 2's. And finally, divide row 1 by 2. And sure enough, we have the same inverse as before. And our original technique is still better. But without a calculator, we did not have a technique for a 3 by 3. So you'd probably say, The original technique is still better when I got to use my calculator to find the inverse, because that didn't take any work at all. And now you set up a huge augmented matrix. You've got lots of space. I want you to try it on your own. So we want to get the identity matrix on the left. A little review. I'll do it here in purple. Well, I'll color code it all the way. So I'll start with blue. You want to get those two zeros first. This 0 second. These to be zeros third. And that 0 fourth. Someone might say, well, the zero's already there for 4. It will not stay there once you get the, you have to do it in that order. Numbers will change along the way. Get the 2 zeros in position 1 in the blue position first. Then the 0 in the green position. Then the zeros in the purple position. And finally the 0 in the orange position. All right, I'll put the way that I did the first one up here. Put what I did switch some rows. I don't know why.
Oh my god, this guy actually was 8 matrices. Could have done it in 6.
I didn't need to do all those switching, right? Wouldn't have needed to switch them.
Yeah, okay.
I got that. I did the last one.
I have some answers. I was in the middle column.